Hey guys, welcome back to lecture series on Fourier transform. I have uploaded plenty of the videos in our channel. So if you are interested to see this video, go and check in my playlist. In my today's video, I'm going to explain to you all one of the example which is completely based on the Fourier cosine transform, and it's an inverse transform. Okay, so here we have example, find the Fourier integral. Okay guys, you will get the question in your Sppu question paper for finding the Fourier integral. Okay, so you have to figure it out which formula or which result you have to apply here to solve these examples. Okay, now it is way easier to understand as we have cos sx present. That means we have to apply Fourier cosine and inverse Fourier cosine transform. Okay, so we have to apply Fourier cosine transform and inverse Fourier cosine transform in order to find out the final answer. Okay, yes, so we have to find out the integral. That means we have to solve this integral over here. Okay, so what is the standard formula for inverse Fourier cosine transform? Okay, so we apply here inverse Fourier cosine transform. As we have Fourier sine transformation, it is given. Okay, sorry, Fourier cosine transformation it is given. Okay, so what is Fourier cosine transformation? Fc of es. Okay, we write Fc of es as a Fourier cosine transform, which is equal to, okay, Fc of es we write, which is equal to integral over 0 to infinity f of x cos sx dx. Okay, sx dx. Okay, so now see that we can observe here 0 to infinity, it is there, small f of x is there, cos sx is there, dx it is also there. That means we can consider fc of s as this function. Okay, fc of s as this function. That means whenever we have interval between 0 to 1, we consider value 1. Whenever we have interval between 1 to 2, we consider value 2. And whenever interval it is bigger than 2, we consider the value 0. Okay, now let me plot with a real line. I will explain to you all this concept with the real line. Okay, now see that as it is only Fourier sine cosine form, so we consider only limit from 0 to infinity. So we have end here 0, we do not go to the negative value or negative infinity. Okay, so 0 all the way it goes to the positive infinity. Okay, 0 all the way it goes to the positive infinity. Now see that we have pieces of this interval. Okay, as we have piecewise function given, so 3 of the pieces of functions given. Okay, so first piece is it gives the value 0 to 1. That means we have 0 to 1 here. Okay, again 1 to 2 again we have here, and again 2 to infinity. Okay, that means we have 3 pieces of the given interval given. Okay, so whenever we have interval between 0 to 1, we consider Fourier cosine transformation as a 1. Okay, again we consider whenever we have interval between 1 to 2 as a value 2, and whenever we have value bigger than lambda bigger than 2, we consider it as the 0. Okay, so that means lambda means we are taking yes instead of yes, lambda we have yes here. Okay, this one is yes, this one is also yes, this one is also yes. So don't get confused, because this one is just a variable we considering here. Okay, so instead of yes you can take any other variable. Some of the books are given yes instead of yes as a lambda, some of the books are given some another variable. Okay, so you can take anything. So yes I consider here, so yes we have to find out the interval. Okay, yes. Okay, so as we have 3 of this function present here, piecewise function, so let's go for applying inverse. Okay, let's go for the applying inverse Fourier transform. Okay, so what we have, inverse Fourier cosine transform. Okay, so we are going to apply inverse Fourier cosine transform. So let me write the formula here so it will be easier for us. Okay, inverse Fourier cosine transform. Okay, so we are going to apply a formula from inverse Fourier cosine transform. Okay, and which can be written as, so we are solving the integral. That means obviously we are finding that small f of x. Okay, so this one is the solution for our integral. Okay, small f of x, it can be written as, okay, 2 divided by pi. Okay, I'm writing here inverse Fourier cosine transform. Okay, yes, small f of x can be written as 2 divided by pi integral over 0 to infinity capital F c of s. Okay, that means Fourier cosine transform over s. That value we are taking here 1 to 0, between 1 to 0. Okay, fc of s, as we have cosine, so we take cos sx. Okay, cos sx ds. Okay, as we have Fourier cosine present here in the form of s, so we are applying integral over s. Okay, so it is a ds here. Now see that 2 by pi keep as it is. So we are going to break this interval. We are going to break this interval 0 to infinity in the form of 0 to 1, 1 to 2 and 2 to infinity. Okay, so let me write 2 by pi keep as it is. Okay, so we are keeping that 2 by pi as it is outside. Under integration we are breaking this interval 0 to infinity, which is a 0 to 1. Okay, 0 to 1. Okay, fc, capital fc of s, Fourier cosine transform, this one is, and cos sx ds. Okay, plus again break the interval 1 to 2. We are going to break the interval 1 to 2. Okay, so we are breaking interval everywhere because as we have piecewise function, so we'll get the piecewise intervals also. Okay, yes, 1 to 2 Fourier cosine transform fc of s cos sx ds. Okay, yes, so this one is the second break, and now third break, it gives us the 2 to infinity. 2 to infinity. Okay, so what the break gives us here, fc of s cos sx ds. Okay, so this one is the break of three of these intervals, 0 to 1, 1 to 2 and 2 to infinity. Now here we can observe here the value from 2 to infinity. Our interval whenever it is bigger than 2. Okay, whenever 2 to infinity is there, we consider the integral here 0. So obviously this integral gives us the value 0. Okay, this integral gives us the value 0. So we have to solve only these two integrals. Okay, yes, we are going to solve these two integrals. Now let's go for the solving these two integral. Okay, replace the values only. So 2 by pi keep as it is outside. Under integration 0 to 1, whenever we have interval 0 to 1, we take fc of s, Fourier cosine transform over s, we take as the value 1. Okay, so we take it is the 1 cos sx ds. Okay, we take Fourier cosine transform over s, we take it is the 1 cos sx ds, plus again interval 1 to 2, again we take interval 1 to 2. So fcs, so whenever we have interval 1 to 2, we take value 2. Okay, now see that here interval 1 to 2, we take the value 2 cos sx dx, cos sx ds. Okay, yes, and plus last integration gives us the value 0. As we have interval between 2 to infinity, value it is a 0 here. Okay, yes, this is just the replacement of the values. Okay, so complete here bracket. Now go for the solving integration over 0 to n cos sx. Okay, so we go for applying integration only. 2 by pi keep outside as it is here. Okay, under integration, okay, cos sx, what is the integration of cos sx? We write the integration of cos sx as a sin sx. Okay, cos sx has integration sin sx, and sin sx has an integration minus cos xx. Okay, and we have to differentiate that sx again at the denominator. Okay, yes, so integration of cos sx sin sx and divided by derivative of sx is s here. Okay, yes, so we apply limit over 0 to 1. Okay, plus again that 1 it is constant. Okay, that 2 constant, take it outside, it doesn't affect in our given integral. Okay, so take 2 outside here. Cos sx integration sin sx divided by differentiation of sx, which is s here, bracket complete. We have interval 2 to 1. Okay, so this one is our given interval. Okay, so now see that we have to apply one time as we are taking integration over s. Okay, we are taking integration over s, we are taking integration over s. So that means we are taking denominator differentiation with respect to s itself. Okay, that means sx has a differentiation x itself. Okay, yes, sx has a differentiation x itself. This one is also x, so don't get the confused. Okay, Mostly where we get the confused whenever variable get replaced now, only in such a case we get the confused here. Okay, yes, it is one of the easier calculation. So 2 by pi under bracket sine we replace now integration with respect to s, so only the replace wherever you found s. Okay, wherever you get the s, replace 1 minus replace s as a 0. Okay, yes, so what we do, sine 1 into s. Okay, I am going to replace s as 1. Sine 1 into s, x means sine x. Okay, divided by x as it is, we are not going to replace the value for x. Okay, we are going to replace only s. Okay, minus replace s as a 0, that means sine 0 into s means 0, sine 0 is a 0, 0 upon s means it goes to completely 0. Okay, yes, plus under bracket here 2 remain here as it is. Okay, now what we do, we replace s as a 2 first and s as a 1 later. Okay, so sine 2 times x divided by x. Okay, sine 2 times x divided by complete divided by x. Okay, yes. Okay, so I replace s as a 2 minus replace s as 1, then we write a sine x upon x, bracket complete. Okay, so now see that how I have solved this example integral. I kept 2 as it is here, applied limit s as a 2 and then s as a 1, and just need to replace the values over here. Okay, and bracket complete. Let's go for solving a further step. 2 by pi sine x upon x, sine x upon x here. Okay, plus 2 times sine 2x upon x, 2 times sine 2x upon x minus 2 times sine x upon x. Okay, bracket complete. So what I have done, I just multiplied 2 under bracket here to this step, both of the steps. Okay, yes, and this one as it is here. So 1 times sine x upon x minus 2 times sine x upon x. So what we get here, so 2 by pi keep as it is outside. Okay, 2 by pi as it is outside here. 2 sine 2x by x as it is, 2 sine 2x by x as it is. Okay, this step as it is, sine x by x minus 2 times sine x by x minus 1 times sine x by x. Okay, that means here we have 2 times sine x by x and here we have only 1 time sine x by x. So if we take their subtraction, okay, so we get the minus 1 times sine x by x here. Okay, yes, so this one is our small f of x. Okay, this one is our small f of x. Okay, yes, so as we have denominator same, take it once, so you can keep as it is also. This one is your required answer, but if you want you can solve further. Okay, 2 sine 2x minus sine x divided by x. Okay, this one is our required Fourier integral. Okay, this one is our required Fourier integral. I hope you all have understood, guys. It's one of the easy solution, just need to apply some short result for finding the solution. So for your reference you can see my entire solution over here. It is one of the easier, guys. So even after, if you found anything confusing, difficult, let me know in my comment section. I will come up with a similar video. Okay, and if you have any demand or if you have any doubt, let me know in my comment section, guys. I will upload similar videos in my channel. So thank you everyone. Thank you for my today's lecture.